Hello everyone, I'm David and welcome you to this talk about our work on PASCAL, a collaboration technique between non-collocated avatars in large virtual environments. Our research is inspired by prior collaborative virtual environments such as Loki by Torabi et al., where a remote instructor can help a learner by interacting with the learner's remote environment. To show further contextual information, the instructor can also switch perspectives to share their environment to the learner. While collaborators in Loki engage in tightly coupled collaboration, large CVEs also allow for loosely coupled collaboration, in which users can work on their own individual parts of the environment, such as, for example, in offering environments as presented by Xia et al. With spacetime. Transitioning from loosely to tightly coupled collaboration and back can be very difficult, as it often requires individual navigation and can lead to a loss of spatial awareness and contextual information. Gilbert et al. Investigated this transition in detail and proposed a theoretical framework for facilitating these mode shifts. The overview stage allows loosely collaborating users to become aware of the user's placements and status within the surrounding environment. The check-in stage allows users to connect with other users within this virtual environment, starting the transition to a more tightly coupled collaboration scenario once consented. From there, users can enter the visit stage to temporarily jump to their collaborators part of the environment, after which they can either decide to return to their original position or stay permanently for further tightly coupled collaboration. We embed our system in this framework and present two novel techniques for the check-in phase, which focus on increasing contextual information sharing. At the start, users are engaged in loosely coupled collaboration within a large CVE. They can then use a virtual tablet, which shows an overview of all connected users and allows them to interact with each other, mediating the transition to further collaboration. You can see this in video form here. Users can select which peer they want to start a session with and check in with them. The peer then gets a call on the tablet, allowing them to accept or deny the request. If the call is accepted, users enter the check-in phase with one of our techniques. For video conferencing, a virtual video and voice call is started. This is an intuitive technique with which users are familiar from the real world. Virtual video and audio is streamed via WebRTC to all other users. Users can therefore share their environment or themselves. They can use a camera swipe functionality to show more of their surroundings, and they can also do individual navigation with the tablet to show details. Alternatively to video conferencing, users can join in a PASCAL session. For that, the system creates an adjustable sphere between participating users, here for user 1, here for user 2, mapping the space within the sphere together. We should visualize the system a bit more schematically. We have here user 1 in a room and user 2 in a room, and user 1 wants to place this piece within this cube. User 2 knows how to place this piece correctly, so user 1 starts a PASCAL call with user 2, sharing their environment and giving user 2 the option to see the contextual information of this environment. User 2, being the expert, knows how user 1 should place this cube, and therefore suggests a manipulation, creating a parallel object. This parallel object is reflected back to user 1, who then sees the suggested manipulation. Going back to the previous image, we have here the red user sharing the environment, we have here the blue user receiving the environment. Both avatars are shared as parallel avatars, so users can interact with the avatars of the other user. Additionally, the red user is sharing their environment as ghost objects to the blue user, as can be seen here, as redly colored ghost objects. Additionally, the blue users can enact manipulations on the ghost objects, creating a parallel object, which is then shared back to the red user. Users can also mediate the PASCAL bubble and accept the PASCAL call, which then creates a PASCAL bubble for both users. You can see here in the video. And the top user is now streaming the environment to the bottom user as ghost objects, and the bottom user sees the ghost objects of the top user. Users can adjust the PASCAL bubble to their liking so that it fits better in their environment, and then interact with the objects, which are then lively streamed to the bottom user. The bottom user can also interact with the objects, creating parallel objects and suggesting manipulations to the top user. For example, as can be seen here, parallel objects are then created. We evaluated these techniques in a multi-user study We used the within subject design for the study and had 24 participants, 4 of them female, 20 male, aged between 19 and 35. We grouped those users into 12 groups of 2 and presented them with 2 conditions. First condition was a video conferencing scenario, the second condition, the PASCAL sphere. Users had to solve a Soma cube puzzle together. A Soma cube puzzle consists of 7 pieces distributed through the environment, and the users had to put them together to form a 3x3 cube. One user was always the expert, in this case the top user, seeing the solution within their environment, whereas the bottom user was the solver, needing to place the correct pieces in their solution cube. For that, users engaged in the video conferencing condition, and the bottom user here was sharing their environment to the top user, and the top user was communicating which solution piece to place. The solution piece itself was not streamed directly via video or PASCAL to not make the solution too easy. So users still had to communicate. In this case, the user finds the correct piece, travels back to the solution cube, and places the piece at the correct position. Once the piece was correctly placed, roles alternated, and the bottom user became the expert, whereas the other user became the solver. For PASCAL, the same applied, and remember the scenario we had before, where the bottom user was suggesting the manipulation to the top user, and in this case, the top user then follows the manipulation, placing the piece in the solution cube, therefore solving the step, and roles were here also alternated, and the top user now was the expert seeing the solution, whereas the bottom user shared their environment with the top user and had to place the piece within their cube. For PASCAL, we have here the expert suggesting a manipulation in the solution cube, and here we have the solver following these manipulations with the correct piece, and the contextual information that's being shared through the parallel object helps the user to actually place the piece correctly. Once the piece is correctly placed, steps also alternate, and now the top user becomes the expert and the bottom user becomes the solver. We posed 3 research questions and corresponding hypotheses. Our first research question asked whether PASCAL was more efficient than virtual video conferencing. First, we hypothesized that PASCAL has lower search, orientation, and step and task completion times than video conferencing. The search time we measured as the time that a participant needs to find the correct piece, whereas the orientation time is the time that the participant needs to orient the piece correctly in the solution cube. Our results showed that users took less time to find the correct piece with PASCAL and less time to orient in the solution cube. Additionally, users were able to finish the steps faster on average and were faster in solving the complete task. All results were significant with medium and large effect sizes. Our second research question evaluated the user's task load, and we expected PASCAL to have a lower task NASA TLX score than PASCAL. For that, we measured the raw TLX questionnaire. However, we found no significant differences in the TLX score. Our last research questions asked whether PASCAL increased ease and clarity of communication, as well as the sense of co-presence. For that, we posed a custom questionnaire to our participants. Additionally, we evaluated the SSQ, hypothesizing a similar level of cybersickness. Our results show that participants found it easier to communicate via PASCAL and reported a higher clarity of communication, as well as a higher sense of co-presence. We found no significant differences in the SSQ score, indicating that neither technique is worse than the other, whereas we found significant differences with medium and large effect sizes for our custom questionnaires. To conclude this talk, I will present a summary of our contributions. We implemented and evaluated 2 techniques for transitioning between loosely and tightly coupled collaboration modes, which facilitate the sharing of contextual information. Our first technique focused on giving users a very intuitive virtual video conferencing solution with which they are familiar from the real world. Our second technique leveraged the potential of virtual reality to create a PASCAL sphere which allows the additional sharing of contextual information through parallel and ghost objects. In our multi-user study, we found scientific evidence that both techniques empower users to solve context-dependent tasks, but we also found out that PASCAL performs significantly better in terms of tasks and step completion times, as well as improving the sense of communication, clarity, and co-presence in comparison to video conferencing. Thank you for your attention and listening to this talk about our work.